Hello again. In this video, we're going to go over local maximum values and local minimum values. So let's go over the formal definition first for both of them, and then we will go over an example. So here's the definition of both of them. Suppose C is an interior point of some interval I on which f is defined. If f of C is greater than or equal to f of x for all x in the interval I, then f of C is a local maximum value of f. But if f of C is less than or equal to f of x for all x in I, then f of C is a local minimum value of f. Now, before we look at an example, I want to talk about something that you should be aware of. When someone asks you to find a local maximum value of f, it's actually the y value for the function, because it's f evaluated at C. If they ask you for the location of the local maximum value, the location of the local maximum value is at the x value, and in this case, the x value is C. Same thing with local minimums. If I ask you to find a local minimum value of f, then it's f of C because it's the y value. So the local minimum refers to the y value. And if I ask for the location of the local minimum, then it's at the x value. And again, the x value in this case would be at C. So be aware of that distinction. All right, so having said that, let's look at example 2. Now in example 2, we're given the graph of this function, and notice that it's defined on this closed interval from A to B. And what we want to do is identify the location of the various maxima, and local minima. Now notice we're going to find the location of the local maximums and local minimums, which are the x values. Okay, so if you look at this function, local maximums occur at Q and at S, and the local minimums occur at P and R. Now, why is that? Okay, well, to be a local maximum, let's talk about the local maximum. To be at the location of a local maximum, first of all, C must be an interior point of the interval. So what do we mean by interior points? Okay, notice this function is defined on the closed interval from A to B. The interior points are the points in between A and B. A and B are called the endpoints. A is the left endpoint and B is the right endpoint. So they're not called interior points, right? Those are called endpoints. The numbers in between in this interval are called interior points. Okay, so Q is at an interior point, and the reason it's a local maximum, or the location of a local maximum, is because if you draw a little interval containing Q, right, around Q, so say it starts here and it ends here, then f of Q is the largest y value in that interval. And that makes it a local maximum value. Same thing with S. If you draw a little interval around S, then f of S is the largest y value in that interval. So f of S is a local maximum. And then, of course, local minimum is a very similar idea. P is a local minimum because if you draw an interval around P, then f of P is the smallest y value in the interval. Likewise for R. If you draw an interval that contains R, around R, then f of R is the smallest y value in that interval, and therefore it's a local maximum. F of R is a local maximum. Okay, so just be careful about this first part of this definition. In order for you to be at a local maximum or local minimum, C must be an interior point. So A is not considered a location of a local maximum. And neither is B. B is not the location of a local minimum because they're endpoints. Okay, so let's talk about how we find local minimums and maximums. So there's actually two different ways local minimums and maximums can occur. Okay, the first way it can occur is when you have a turning point that's smooth. This is called a turning point. It's smooth. This turn is occurring in a smooth fashion. And I think you can see that you do have a local maximum right at C. So that's one possibility. You have a turning point that's very smooth. The other possibility is, you can see here, C is the location of a local maximum. The turning point is abrupt. And that's called a cusp. Sometimes we call that a sharp corner. You can see that's the location of a local maximum, right? So that's the other way that you can get a local maximum. And this is also true for local minimums as well. Local minimums can occur, you have a smooth turning point like this, or an abrupt one where you have like a V shape. Now, why is that important? Because if you look at the derivative at C here, the derivative at C would be the slope of the tangent line. So you can see the secant lines approaching this tangent line, and right at C, the tangent line is horizontal. And so, of course, the slope of that tangent line is 0, and that means the derivative at C is also 0. And so f prime of C equals to 0 at this local maximum. Then down here, when we have this one, f prime of C in this case does not exist. That's because derivatives don't exist at sharp corners like this. Okay, so when we go to look for local minimums and local maximums, which we're going to do in the next video, we're going to try and find them by locating the places where the derivative is either 0 or does not exist. Because if we have a local maximum or local minimum, we know it either has to occur at one of these smooth turning points where the derivative is 0, or it must occur at one of these sharp turning points where the derivative does not exist. Okay, so that leads us to a theorem that I want to talk about. So this theorem says that if f has a local maximum value or a local minimum value or local maximum value at C, then f prime of C must be 0 or f prime of C does not exist. And we know that because, again, either has to do this or it has to do this. Okay, in this case, f prime of C is 0. And in this case, f prime of C does not exist. So if I have a local maximum, then one of those must be occurring. Likewise, if you have a local minimum, it can only occur in one of two ways. F prime of C is 0 in this case, or f prime of C does not exist. Okay, so that's what this theorem tells us. Now, one thing I want you to be aware of is the converse statement to this statement is not true. Now, what do we mean by a converse statement? So if you look at this statement, you can think of it logically as A implies B. The converse of A implies B is B implies A. That's called the converse statement of this. So that's the converse statement. So if you formulate the converse statement of this, you would say that if f prime of C is 0 or does not exist, then f of C is a local minimum value or a local maximum value. That statement, the converse statement, is not true. And here's why. I'll give you a couple counterexamples to show you. So if you look at these two functions right here, or the graphs of these two functions, at this particular point C right here, you can see that the derivative at this point is 0 because the slope of the tangent line right there is 0. This is not the location of a local maximum or minimum. So just because f prime of C is 0 does not mean you have a local minimum or a local maximum at that point. Here's an example where the derivative at C is undefined. And I think you can see that because the slope of this tangent line, right here at x equals c, the slope of that tangent line is vertical, and the slope of a vertical tangent line is undefined, right? So f prime of c doesn't exist here at c. Okay? And you can see that that doesn't mean that we have a local minimum or maximum, right? This is not a local minimum or maximum at c. Okay? So the converse of that statement is not true. You need to think of both of these counterexamples to remind yourself of that. So you have to be very careful about this. If you happen to find that the derivative at c is 0, then that does not mean you have a local minimum or maximum at c. This is the counterexample you should think of. This is f prime of c is 0, but that's not a local minimum or a maximum at c. And it's also true that, if f prime of c does not exist, it doesn't mean you have a local minimum or maximum at c. Again, this is the counterexample you need to think of. Right? F prime of c does not exist, but that's not the location of a local minimum or maximum. So if you remember both of these counterexamples, it will help to remind you that the converse of this statement here is not true. So this is not true. We have two counterexamples. Okay, so the last thing I want to talk about in this video are critical points. So because f prime of c equal to 0 and f prime of c does not exist are sort of common occurrences that we're going to run into in this section, we have come up with a special name for locations where that happens. So here's the definition of a critical point. It's an interior point, so an interior point C of the domain of f at which f prime of c is either 0 or f prime of c does not exist is called a critical point of f. So notice that in order for you to have a critical point, C must be an interior point in the domain. It cannot be an endpoint. So that's the first thing you should be aware of. The other thing is you must have f prime of c either be equal to 0 or f prime of c does not exist. If either of those occur and you have an interior point for c, then that's called a critical point. So just to kind of reinforce this idea, this right here, this c is called a critical point because f prime of c does not exist and c is in the interior. It's not an endpoint. It's in the interior of the domain, right, of this function. It's not at an endpoint of that function, of the domain of that function. Then here's a case where f prime of c is 0, and c is in the interior of this function, the domain of this function, and so this is also called a critical point. Okay, so in the next video we'll do some examples where we actually find the location of local minimums and local maximums. So until then, I hope you found this video helpful. Thank you for watching. Bye-bye.